My name is Pannaga Shivaswamy, and I'm from Netflix. And this is joint work with Dario Garcia while he was working at Netflix. The title of my presentation is Adversary or Friend, an adversarial approach to improve recommender systems. There are many different techniques to train a recommender system model from user item data. Typically, we have users on one axis, items on the other, and we have a bunch of observations, which of the users saw which of the items. And then there are various techniques that can be used to train a recommender models, such as matrix factorization, slim model, ease model, variational autoencoder, and so on. The goal in many of these applications is to achieve good ranking performance. And many of these techniques, they work very well on average, but there could be many pockets of users who may have poor performance. In this work, we focus on users with poor performance. And for this, we take an adversarial learning approach. A quick note on the title of the paper is that although the method that we are using is an adversarial approach, it acts benignly. And so although it's an adversarial approach, it can be a good thing sometimes. So that's the motivation for the title. A few highlights about the presentation are as follows. First of all, the user segments where we try to improve are not defined a priori. So they get defined as part of the learning process. We show that naively extending supervised learning approaches to recommender systems may not work well. So we propose what we call as a decoupled adversarial learning approach that works well in practice. And then in the experimental results, we show that we can achieve improved or flat overall performance while significantly improving the performance wherever the baseline models have poor performance. We start with an approach called adversarial reweighted learning, which was proposed for the case of supervised learning problems. In the case of standard supervised learning problems, we have features xi and labels yi, and typically an empirical empirical mean of the loss is minimized. In the adversarial reweighted learning approach, this loss is augmented with a weight, which is learned as part of the adversarial model. The learner and the adversary are set up as a game where the learner tries to minimize the objective while the adversary tries to maximize the objective. The end result being that the learner tries to do well wherever the adversary scores high. And in the paper, in our paper, we show that when we have an adversary like this, it typically gives high scores on dense regions wherever the losses are high. While the methodology in this paper is applicable to many other methods, recommender systems method, in this paper, we mostly focused on one model, which is called the ease model, which predicts each item based on all the other items. It uses a squared loss and it admits a closed form solution. It typically, the ease method typically works really well on many publicly available data sets. The main idea is to learn an item by item matrix such that we predict every item based on all the other items. So here is the objective for the ease model. Xij is the observation for the ith user and the jth item, and xw is the set of all predictions, and then xwij is the prediction for the ith user and the jth item. And then there is a squared loss between the two, and then there is a Frobenius norm regularization. The diagonal of w is set to 0 so that we don't predict an item by itself. Now, if we just take the ease model and use the recipe from the supervised learning approach and try to extend it to an adversarial model, what do we get? Here is the original L2 loss from the ease model. It is augmented with a user level adversarial score. So in this paper, we mainly focus on user level adversarial models. And then there is a regularization for the learner, and then there is a regularization for the adversary as well. The standard way to optimize such an objective is to do a gradient descent on the learner parameters and a gradient ascent on the adversary parameters. And when we have the regularization parameter for the adversary properly tuned, it can achieve good performance. However, this naive approach doesn't really work well, and we will see more results in the, we will see some results in the experimental section. The main issue here is that the adversary scores may not be well aligned with the end ranking task that we may care about. So originally we said that the end goal of the recommender system was to rank the items. A simple adversary setup like this may not be well aligned with that objective. So to overcome that problem, we propose a different methodology, which we call as rank loss based adversarial model, or RLARM, where we decouple the adversary from the learner. So rather than completely tying the adversary with the learner's objective, we learn the adversary based on a more relevant ranking metric, such as the NDCG, and train the adversary based off that metric. However, the adversary would still influence the learning, and the two are coupled, as I'm going to show now. So on the top, we have the learner, and at the bottom, we have the adversary. The learner is still influenced by the adversary in that the losses are weighted by the adversarial model, and the for the adversary, the losses are computed from the model that the learner has at any given point of time. The optimization problem for training RLARM is similar to what I showed before, except that now we have two decoupled objectives, and we do gradient ascent on the learner parameters, and gradient descent on the learner parameters, and gradient ascent on the adversary parameters. For our experiments, we considered 3 large-scale publicly available datasets that have been previously used in many other papers. And those datasets are Movie Lens 20 million, Netflix Price dataset, and Million Song dataset. And these datasets have held out validation and test users. All the hyperparameter selection was done using the validation users, and we measure the performance on the test set of users. We compare the proposed methods against EASE, which is the baseline model on which we built all these adversarial methods. But we also considered another baseline, which is a simple baseline but works very effectively, which we refer to as EASE IPW. So basically, for every user, we count how many of their observations are ones, and then we do 1 over number of observations that are ones to the power of beta, and this beta was tuned as a hyperparameter to optimize the overall performance. And the original EASE model actually admits a closed form solution, and and even if we have user level weights, it continues to admit a closed form solution. So we used a closed form solution even for IPWEs. And then we consider the naive extension, and then RLARM and RLARM NN, which is for the adversary, we use a 2-layer neural network for the adversarial model with a tan hyperbolic activation. So the first result in the paper that we want to discuss is that the naive extension simply doesn't perform any better than the baseline EASE model. So what is wrong with that? So on the left, we look at the we look at different user buckets, and we look at the average loss of the users as defined by the EASE model, as well as the average NDCG performance for those users. With the adversarial models, with the original goal that we stated, we want the adversarial weights to be high wherever the ranking performance is poor. But given the nature of these data sets and the sparsity and the loss that we use with the ease model and so on, it turns out that the average loss for users are also high wherever the NDCG performance is high. So the adversary, rather than weighing those users whose performance is poor, the adversary ends up weighing those users with the best performance even higher, and it doesn't result in any meaningful differences in the results. Next, we look at the results on the other set of methods, is IPW, RLARM, and RLARM-NN. So on the right, I have a table where I show the overall performance. The ease baseline is 0.420. This is NDCG, and then ease IPW, RLARM, and they all achieve statistically significantly better results, and RLARM and RLARM and then achieve significantly better even compared to IPW. But that's just the overall picture. The more interesting part is if we dig deeper into the results on the left plot. On the x-axis, we bucketized users based on the performance of the ease model. So when you see 10, it's the bottom 10% of the users with the worst performance by the ease model. 20 is bottom 20% with the worst performance from the ease model, and so on. And on the y-axis, we see how much improvement we obtained from each of these different methods compared to the baseline. And we see that, first of all, ease IPW itself achieves a significant improvement, but both RLARM and RLARM-NN achieve even stronger results compared to ease IPW. On the Netflix price dataset, the results were not as good as Moviland's 20 million. If you look at the overall performance, both IPW and the adversarial techniques achieved significantly better overall performance. But if we bucketize user and see the results, on some of the middle buckets, we did see improvement, especially for RLARM-NN, but the results were much smaller compared to the previous dataset. Finally, on the MSD dataset, in the overall performance here, we don't see that much movement. But if we look at the bucketized versions of the result, we again see pretty significant improvements for RLARM and RLARM-NN. So in summary, what we have shown here is that adversarial models can be used for improved recommender performance, at least for some of the users. And in the experiments, what we saw is that we can either achieve flat or improved overall performance, but we can potentially have huge gains for segments where the baseline model may not perform that well. The main idea to get it to work was to decouple the adversary from the learner and align the adversary with an end ranking metric that we cared about. And there are many interesting potential future directions. We mostly focused on a user level adversary. The adversary could be an item level adversary or a user item level adversary. We considered only 2-layer deep neural networks. We could go deeper. And also, there is an intriguing possibility because there is a baseline which works well at some parts, and then the adversarial model which works specifically well where the baseline model fails. There may be an opportunity to combine those models and form an ensemble and hopefully do better everywhere. Thank you very much.
Excellent. Thank you. So there's a bunch of questions on Slido. I don't know if we're going to be able to get through them all, but there's a couple asking if you could clarify what the adversary is actually learning and what's causing it to perform better than the baseline.
Yeah. So basically, the adversary is learning to score those users where the model performance is poor, and it essentially puts a higher weight wherever there is a cluster of users that have poor performance. So rather than focusing on an outlier example that may be having poor performance, we actually go into some depth in the paper. Adversary puts a higher weight wherever there are larger cluster of the users that have a systematic high loss, and that is what typically helps. I think if you just put all the weight on the outliers, that may not do the trick.
Excellent. And I guess maybe we have time for one more question. So I guess one of the other questions is, how does this model compare to other GAN-based approaches like CF-GAN or GAN-MF?
Yeah, I think unfortunately, we haven't done those comparisons. Yeah, if there are some concrete pointers, I would be happy to chat offline about those.
Excellent. Well, let's thank the speaker again. There's a bunch more questions, and I'm hoping you can answer them on RecSys Hub after.